All right, so today what we're going to do is we're going to look at several of these free responses from different APs and kind of look at how we would use all of the knowledge that we've learned so far in AP Calculus to answer these questions. You always want to make sure that as you are reading through the free responses that you kind of pay attention to some important things that they're going to tell you. So let's read through it and let's see what we want to highlight. So we have a particle that's moving along the x-axis. We're given the velocity, okay, so we want to make sure that we recognize that this is a graph of the velocity, 0 to 6. This is a differentiable function, v of t. I want to highlight that because, of course, knowing that v is differentiable will give me information about the fact that it's a continuous function. It also gives me the fact that it's an integrable function, and there's also a derivative, and so it's meaning we can work forwards and we can work backwards with it. We may need to use that for some of our theorems. All right, we're given that our velocity is 0 at 0, 3, and 5. So let's kind of do a little highlight here at 0, 3, and 5 is where we're going to have our velocity being 0. And then we also have the graph has horizontal tangents at 1 and 4. So 1 and 4 is where we're going to have horizontal tangents that they're telling us. So we'll put that down so that we kind of have that information highlighted so that we can use that. They also give us that the area of the regions, and they're giving these as positive values. The area of this region is 8. The area of this region is 3. And then if we drop down here, the area of this region is going to be 2. And now another important fact, there's a lot of things that's in this problem that you have to be paying attention to, which is that they're giving you at time 0, the particle is at x equal to -2. So they're giving me information about where I started from. And you'll remember that we're coming in this idea of integrals as net change is that where I am is equal to where I started plus the net change from where I am to where I started on that function f prime of x dx, where you have the derivative in there. So here's your net change on the function, where you started, where you ended up. And so we want to use that idea, and they're giving you this so that you are using the where I am is where I started plus the net change from where I started. All right, so let's take a look at the actual question. So that was a lot of things in the actual question that you should read and pay attention to and highlight before you go on to the actual parts of the question. All right, so let's see what we're going to do here. So in part A, we want to find the time and the position when the particle is farthest to the left on this closed interval of 0 to 6. So what that's telling me is that I'm looking for a max farthest to the left. Well, actually, that would be a min since I'm on the left side. So I'm looking for a min, and it's a global min, and it's a global min on the closed interval from 0 to 6. So hopefully the alarm bells are going off in your head, and you're going to remind yourself that this is an EVT problem. Okay, let's read ahead. Let's see what else we're going to do. So for part A, planning ahead, we're going to be doing the extreme value theorem. So we're going to have to think about our conditions and what are the parts of running that theorem. Now notice that it also says in here, I'm going to highlight this before I move on, that what I want to do is find both the time and the position, that there are two things that you need to find for part A. So we're going to note that as we're working. All right, let's see what we're going to do in B. For how many values of t between 0 and 6 is the particle at x equal to -8? For how many values of t is the particle, this is the position of the particle, right? When is the particle at x equal to -8? So we're looking to show that there exists. We're looking for existence. So this is one of those existence theorems. And we're looking at the existence of when the particle's position is at -8. So if we want to call the position function s of t, We want to know S of t equals -8. Is there a time on the interval? So does there exist a, say, C in the interval from, what are we doing, 0 to 6, for which the particle's position is -8? So we're looking for an existence theorem. Now, since you have to start thinking about, is this going to be mean value theorem? Is this going to be the intermediate value theorem? Which theorem are we going to look for that? So I'm going to leave that for a moment, and I'm going to come back to it, and I'm going to let you guys think about that and think about what you feel is going to be the theorem that applies in this situation. And also, paying attention to the fact that what you know is that you know the velocity function. Now, I will tell you that sometimes, like for something like this, you may be using items in Part A to help you answer Part B. Now, let's kind of recap again. In our procedure for finding and applying EVT, we are going to be making a chart, and in that chart, we're going to have values of time and values of the position function because we want to know farthest to the left. And so we might be able to use those values of S of t to help me determine if S of t equals 8. And so because of that, I'm leaning toward that I'm probably going to be using an IVT on this, using the values that I create in the chart in A. All right, now let's look on to C and see what C is asking me for. On the interval from 2 to 3 is the speed of the particle. Let's highlight that because that's important. We're not talking about velocity. We're talking about speed. Is the speed of the particle increasing or decreasing? And remember that when we look at this one, we want to be looking at the acceleration of the particle on the interval from 2 to 3, and we need to look at the velocity of the particle on the interval from 2 to 3. And we want to see what that is doing. And if they're the same sign, then the particle speed is increasing. And if they are different signs, the speed is decreasing. So that's going to be our target for part C. All right, and then the last question, D, says during what time intervals, if any, is the acceleration negative? Is the acceleration negative? So and remind ourselves that acceleration is the derivative of the velocity curve. And we know that, and so it's the slope of the velocity curve. And so we know that what we're looking at is we're looking at where V of t is decreasing, where V of t is decreasing. All right, so what we've done right now in this example 4 is we've set it up so that you kind of have a background for what you're going to do in each part. So now I'm going to pause the video and I'm going to let you guys actually try to do the work for this and then unpause it and come back, and then you can check and see how your answer compares and you can grade your free response. So pause it and now go work this free response and come back. Okay, so now we're going to take a look at the solution that I have for this. So for this first question, remember we were doing the EVT, extreme value theorem. The function that we were doing the EVT on is going to be the, I'm going to switch over to this version so I can write on it, that we were going to be doing EVT on the position function, S of t. So our target for what we wanted to have continuous, the function that you need continuous to meet the requirements of the theorem, is this part right here. So we wanted to make sure that we have S of t being continuous. And so here's kind of how we went through the process of finding that S of t was continuous. This is what we were given. So you need to at least say we were given V of t is differentiable. Now, I will say that on the AP, provided all this middle stuff, you don't necessarily need to have. What you need to say is that given V of t is differentiable, we know S of t is continuous on 0 to 6. If you give the intermediate steps, that's fine, but you have to at least start with the fact that V of t was given as differentiable and end with the conclusion that S of t is continuous on the closed interval 0 to 6. Now, the reason why is that if the velocity function is differentiable, that implies that the velocity function is continuous. If the velocity function is continuous, we know that the velocity function can be integrated. And if the velocity function can be integrated, that means we must have been able to take the derivative of the position function S of t, which means that S of t is continuous. But as long as you say V of t is differentiable, implies that S of t is continuous on 0 to 6, you will check that box for meeting the requirements and the conditions of the extreme value theorem. If you also said that S of t was differentiable, then you are going to get dinged because you cannot give extra information. You have to know that EVT only requires that S of t be continuous on 0 to 6. So you don't want to make it sound like you thought differentiability was a condition of the theorem. It's okay to be kind of in the stream saying these are the reasons why, but what you need to make sure is you recognize that the requirement for the theorem is that S of t is continuous. Your critical values of S of t are going to occur when the velocity is equal to 0. And they have to also be on the interval, and we don't include, well, we're going to include endpoints on that, but remember, critical values have to be in the interval. So your critical values are 3 and 5, but you do remember to include your endpoints in your EVT chart. All right, now, we were given S of 0, and now we're using that idea that where I am is where I was plus my net change. And this definite integral that we're putting in here is calculated using the areas, except you have to remember that because it's the definite integral that this is the signed area, that you have to include negative when you're below, positive when you're above, or reverse it when you're going backwards. So -2 plus the net, or the how much I accumulated in area from 0 to 3. And since that was, if you take a look at our picture up there below the x-axis here, while the area is 8, the net area, the net in this section is going to equal -8, right? So that gives us -2 plus -8, we're at -10. Now, I could go back and start at -2 again, but once you're doing this, just go to the previous one. Where I am at 5 is where I was at 3, plus my change from 3 to 5. So we add in a positive area for that because it was above. And then where I am at 6 is where I was at 5, -7, plus the change from that. And again, we add that back in. We put in a negative because that one was below. And then we look at our chart and we figure out where we are farthest to the left, and that happens when we are the most negative. So it's most negative at 3, which would be this one right here. And notice I gave the time and the position because they asked me for both of those. All right, now once you have this chart, then that's where the IVT is going to come in. Now, the requirements for IVT are that you have to have the S of t function be continuous on the closed interval. We already had that. We already set it up here. You can restate it, but I don't have to restate it because I already set it in part A, and they will use part A and part B. But if you did restate it in part B, that's fine. And there are 3 times when x equals -8, when there are 3 times that exists, because by the IVT, since S of t is continuous, technically I should have said there on the interval 0 to 6. And -8 falls between, I picked S of 0 and S of 3, S of 3 and S of 5, and between S of 5 and S of 6. So I'm using these values that I have here in my IVT. So this is an example of how we are using part A for B. All right. In part C, your velocity is negative because the graph that you were given was below the x-axis on this interval, and the acceleration was positive since v of t was decreasing, so speed is decreasing. They are opposite signs. And again, acceleration is negative on these intervals because v of t is decreasing.